Okay, so there's SPSS and SAS data sets that we make available. There's also a comma separated variable file that is made available. What we've run into with this study is that we have a lot of people that use Stata. Anybody use Stata here? Yeah, so you'll figure out how to import it. It's not in school-based assessment, which is what we've done for the most part. People use SPSS and SAS, and in the economics world, people use Stata. So. Huh? You use Stata also, the commission, yeah. So, no SPSS also, yeah. So. Yeah, so that's why you also have the CSV file, so you can import them. And I suppose Stata with Stata you can import from SPSS and from SAS. Anyway, the main point here is that we give you data for free in SPSS and SAS. And where you use them and how you use them, then that's your department. In terms of the records included, so these are the records that are included. Any those that are 16 to 65 years old, completed cases, and they have to pass validation, adjudication, and waiting. Meaning, they have to be a case that makes sense to be in the data file. So this includes cases with partial or minimal information, such as those with literacy-related non-response cases, and breakouts, meaning people that were taking the test and all of a sudden stopped for whatever reason, but there was sufficient information to give them a score. And later today we'll talk about how is it that we give people scores when they haven't taken or completed the assessment. The set of cases across databases is identical in general. One exception applies to the Canadian Post. Some cases were excluded and corresponding weights were loaded onto others in a particular domain to comply with Statistics Canada's minimum weight standards. Meaning, they basically have regulations to be able to report some data to avoid identifying people in the data sets. So they do some tweaking of the data, some minor changes that are inconsequential to the analysis that you will be doing. It will not be impossible to replicate reported estimates precisely, and this is what you said. This should not have no practical relevance and should not affect the agreement of rounded estimates published by the OECD, those produced by Data Explorer, and those made on the basis of the public user file. So if you analyze, regardless of the data set that you use, you should be able to come up with the same numbers, same results. Questions? So the data underlying the Data Explorer and the user files contain different sets of variables. They all contain a set of the total user files has 1,300 variables altogether, and that's because it has all the item responses, has timing information, etc., which are not saved onto the Data Explorer because you don't. It's not meant to be used for those types of analysis. And that's what it said. The variables included in the public user file relate to the individual cognitive item scores and process information. So
the data sets that you provided for us on the download, those are the puffs.
Those are the puffs, yes. Yeah, public user files, and those have everything. Those have everything except the confidential information that it's only in the Data Explorer.
Yeah.
So there's there's that intersection of the there's an intersection and there's some unique stuff in each one of them. So variable groups, base information, demographics, and background questionnaires. So here you have identifiers and these position codes. And these position codes were basically the routes or the different pieces and components that the person took. The background questions which have that number, that code right there, is the same code that you will find in the background questionnaire. So if you look at that code right there, that's the variable name that we'll use in the puffs in the data explorer. So it will allow you to find variables in the database. So then you know, I'm not gonna go in detail over this, but there's a whole bunch of variables that will allow you to derive variables, derive earnings information, background information derived from original coded variables, etc., etc. So, for example, these are age groups in 10-year spans or 5-year spans. You know, so you want to do 16 to 25, 26 to 35, and so on, or you can do in 5-year spans with 16 to 21, 22 to 26, etc., etc. So you have skill scores for the some of the skills use information. Again, these are the names of those variables. You will have some trend information, some trend variables. So if you're going to be mixing the PIAAC data with IELTS or the OLS data, you have some variables. Coding routing, you have derived portion information, etc., etc. You will have, these are the scale scores in literacy, numeracy, and problem solving. Notice here that there's 10 of them, and we'll talk about that later. The total correct scores for the reading components. So, paragraph comprehension, sentence processing, and vocabulary. Read. You have the times that it took them to answer those components. And then you have variance estimation and full weight replicates, and then we'll talk about this later when we talk about weights and the sample design. Background questions and variables derived from it. So here's sort of like the codes that you will find in the variables. So all the education and training begin with letter B. Status and work history begin with letter C. Current work with the letter D. Previous last work with letter E. And that just has to do with the section of the questionnaire where the variable was found. A number of variables were excluded in consultation with the OECD and the BPC, the Board of Participating Countries. And these were variables that had to do with no little analytical utility, intended for internal or interim purposes, national questionnaire material, security of item material, protection of personally identifiable data, etc. Full detail provided in technical report, chapter 23. So if you want to know exactly what was excluded, you can go to chapter 23 of the technical report, and you will have that information there. The database underlined the data explorer and the proof was subject to suppressions at the cell or column level for individual countries demanding such suppressions. The majority of these instances relate but are not limited to detailed age, language, country of birth, region information, detailed education information, etc., etc. Suppressions may differ between the Data Explorer and the PUF, the public user file. Some people get worked up about the suppression. They say, "Oh, what are you hiding? What's there?" And let me just tell you some words that, I mean, the reason why it is in our best interest to publish as much as we can. And what we don't publish is because we really can be published. And we make the best honest effort possible to make sure that most of the information is published without risking individuals or risking the projects, So us insisting on publishing some type of information, for example, in the case of Australia, would mean that Australia wouldn't participate. So it's better to have Australia participate and then have you get the data from Australia from Australia itself, than than not to have their data at all. So that's sort of like the balance that there's nothing, there's no conspiracy. It's mostly age, education level, language, country of origin that we're suppressing on very specific cases to avoid identifying people. We're not changing distribution. In doing so, we don't change distributions. We don't change, group statistics, etc., etc. So, consequences of the suppression is public users might not be able to fully replicate particular table figures and other exhibits in the international report. But again, I've been doing this for 20 or so years, doing these trainings, and the differences are at the rounding level. Questions about this? Okay. Representing valid and missing data. One thing to be careful when using this data is that there's sort of like three key types of missing data. There's data that's missing by design, which means that, for example, questions that have to be skipped based on previous questions, like, were you born in the country? Yes. So then there's a question that says, how old were you when you arrived in the country? Well, that is missing by design sometimes, because if you were born in the country, you didn't, that question is unnecessary. So, as a result of the response process, as a result of national adaptation, survey, logistics, processing, or analysis. So there's different reasons why some data might be missing, and that's why you see all those codes, skip by design, you see not administered, you see omitted. No missing value imputation was intended or attempted, except for the imputation of earnings for precise and or broad categories. So you'll find some of the earning variables there's some imputation that was done there, but other than that, there's no imputation that's on at the specific individual variable level. Respondents with literacy-related dispositions were not administered the interview, and as a result, we didn't compute plausible values, and then they're marked accordingly in the background questionnaire. So in the data file. So for example, people that don't take the problem solving. So we cannot assess the problem solving skills because they can't read the language. So those people are not classified and they don't get a problem solving score. So I'm going to show you one of the analysis that you could want to do is you want to see the percent of people by proficiency level, and then exclude those that didn't actually take the problem solving that could have taken it. That would be the case, for example, of if I lived here in the Czech Republic and they come to my house and I respond the background questionnaire and I might be able to do the core, but then I don't speak Czech and the problem solving will be in Czech. So it would be unfair to assign me as a low problem solving person because I wasn't able to take the problem solving questionnaire in Czech. And that's why that's LR now, literacy related non-response. Anyway, more details about missing data. There's sort of like a thing that you need to keep in mind, and is this, which is there. Valid skips, don't knows, refuse, and then not stated inferred, and then not administered, not applicable. And those are the codes. These are the codes that are used in the data files that you will find, and those are the labels. So when you're doing analysis, check for those. Okay, make sure that you're not using missing information should be missing, using it as a value. Questions about this? About the data? Yes.
No, just a question, but just a comment that it seems like it's very important also to read the technical report, because I find, for example, for Norway, a commentary there that Norway was not able to provide non-response adjustment cells due to confidentiality concerns. Therefore, Norway self-reported the correlation between literacy scores and background non-response adjustment variables and breaking variables as 0.48 for literature. Norway did not report the correlation for numeracy, therefore 0.48 was assumed for numeracy. So it's important to obviously read this technical report.
Yeah, for those in the back that are hearing this, the comment is that there's a technical, what chapter is that you find it?
This is 16.
That there's in working with the data, you want to, as you can imagine, doing this study across 24 different countries is complex. It's complicated. We try to standardize as much as we can, but there are nuances, in terms of what actually happened in one country. So, so she's pointing out at something that happened in.
It's the indicators of the quality of the sample data. This
indicators
is chapter
of
16.
Chapter 16. So let's take a look at that. And that will be in the technical report.
Technical report, yes, chapter 16.
So there you have, I think there will be a table with countries. Let's take a look at this actually, This is non-coverage. And then we have Denmark, we have 5% of people that are inaccessible. And let's take a look in Norway, 0.4%. So I guess the Danish probably, anybody from Denmark here? No. The Danish probably included 5%. Estonia, 2.8%. And somewhere down here, it would tell you.
If you look at table 16 to 5.
Table 16, is that what it is? 16.5?
Yeah, there's a footnote.
Yeah, I'm not sure exactly what that means, but yeah, I think what they do is they do. This has to do with the bias response analysis. that with the bias response analysis, that some countries, their non-response rate is pretty high. So one of the things that the country has to do is provide background information in support that non-response doesn't affect the overall estimates for the country. So that's what that. But the lesson here to be learned, and I mean I don't know all the specifics of every single country. The lesson here is that there's a technical documentation where details like that for each country are specified, and you want to review that to make sure that that you're using and you're making the proper inferences of the from the result. For example, you know, I mean, two obvious examples when you look at the Belgian file, that doesn't include the French-speaking Belgians. You know, that when you look at the UK file, that's only England and Northern Ireland. And from there, there's a whole bunch of others. There's a series of other situations and conditions that are explained and documented in the technical reports.
But is it documented, the non-response rate by country?
Yep.
Okay.
Yeah, and that's what you have. You have that, the one that you show you, the coverage. And here you have the response rates.
Okay. Very high.
Yeah, I mean, they're very high for a household survey. They're very low for a school-based survey. See, I'm looking at the overall right here.
Ah, okay, yeah, no,
Yeah.
yeah.
But even these, you know, these are.
And reasons for non-response, are they documented?
There are many. I mean, and my main reason is, imagine that somebody's trying to chase you to do this. How many of you would do it?
How long does it take?
About an hour and a half or so.
So it's-
Yeah. So again, imagine. How many of you have received a call for people that they want to do a survey of you? And how many of you have actually done it? The Norwegians, maybe. So reasons for non-response: the person refuses to participate, the person is too busy, the person.
So the question was, are they documented?
Yes.
Like these reasons for non-response?
Yeah.
Because when doing an analysis, you need to take into account the reasons for non-response.
Yeah, I mean, there'll be broad general categories, you know, but they won't know in every individual case. And the cases that refuse to respond are not in the data file, so you wouldn't find them there. Okay, questions about availability of data, about PIAAC, etc., about what we talked about so far. Okay, so let's get into another topic. Yes.
For timing values, there are only for reading components.
Yeah. Also for the questions, for the items.
For the items, the background question, which item?
No, for the items that were administered on computer.
Ah,
Yeah.
so in fact we don't have timing patterns for PBA for.
Correct. Right. Okay, so let's talk about the assessment design and implications for analysis. So what does it mean? What does it mean? What is it that we do, and how we do it, and why we do it? So some of the challenges is that the domains are very broad, meaning we want to assess people in numeracy, literacy, problem solving, and then we want to ask them a series of background questions. And it takes time to do that. So we need to, and there's limited testing time, physical and psychological. And I say physical in the sense that when you go to a school and you're doing this in a school, that you want to fit the assessment during the class periods, and when you go to somebody's home, you have to fit this during their lunchtime, or between work and dinner, or after dinner and before they go to sleep, or in the morning before they go to work. So there's a period where it's limited, and then psychological, because if you ask people too many questions, eventually they get tired and they don't respond well. Which is why whenever we do these workshops, after every hour, hour and a half, we take a break. Because if I kept talking and talking and talking, you would be like, right? So, and it's funny because when you're doing the workshops, everybody's quiet, and then occasionally what happens is one or two people get up to go to the bathroom or to get a glass of water, and you realize, okay, I'm losing them, and then that's like the good time to usually to take a break. So there's limited time, physical and psychological, and we don't want fatigue to set in. We want to be able to that person to be fully engaged and participating. So we need to administer the items in a sensible way, and then reconstruct the numbers to get numbers that actually represent the thing that we're trying to measure. So we do something called sampling, and many of you are familiar with sampling, somewhat, to more or less degree. And we do this because we have too many people, there's too many items, and it would be too expensive and unnecessary to test everyone on everything. And here I do two examples that illustrate how sampling works and the usefulness of sampling. Number one is the blood sample. And if you don't believe in sampling, next time you go to the doctor and the doctor wants to take out a blood test, tell the doctor, take all my blood out and test it all. Right? And obviously that's not necessary because it will be damaging to you, etc., etc. So we don't need to draw all your blood. We don't need to test everyone and everything in order to know the status of things. And regardless of how tall, short, wide, thin, etc., regardless of your shape, size, age, about the same amount of blood does the trick. Is enough. Okay, so a bigger country, we don't need to draw more people. A smaller country doesn't need fewer people. So we need a particular number of people to get an estimate of a certain precision. And then you'll say, yeah, but the blood is well mixed, always flowing, and that's where the soup example comes into place, because sometimes we make soup, and you put vegetables, and you put meats, and you put the broth, and you put different kinds of meats, and what you do is to know if the soup is ready, is you stir it, you taste the broth, you taste the vegetables, you taste the meats, and then you say the soup is ready or not. But you make sure two things. First of all, you don't drink the whole soup to know if the soup is ready. Number two, you make sure to take pieces from the vegetables, from the meats, and from the broth to make sure that all the components are represented. And in the end, you say the soup is ready overall. Yes?
Yeah.
So, that's exactly how we do it here. We take samples of about the same amount of people within each country, but we make sure that these samples cover the whole domain. So we have vegetables and meats and broth, etc., etc. So some people test on some things, but then we need to make sure to take the results into this design into account. So how does sampling work? We select a few people from the entire population. To those selected, we give a selected number of items, and this is known as multiple matrix sampling. So here's how sampling works, and I hope that you can see that you will agree with me that there's not enough points. So we select the pixels here in the picture. That's not enough pixels. This is a little better, and this is better. So the more we select, the better picture we get. But here we don't have to select them all to get the full picture. Here we are selecting, I think, 50,000, and we get a pretty good picture of what's happening there. Right? So, and this is what happens when we take pictures and with the digital camera, so we send it to our friends by email, etc., etc. That if we expand it, it looks awful, but if we shrink it, it looks better. Because depending on the precision that we want to get. So, I'm going to give you more examples related to that. So, in a PIAAC, the population of interest is adults that are 16 to 65. And then there are other special samples by the choice of countries. For example, Denmark had a special sample of people that participated in PISA. Germany had a sample of adults that are 66 years old or older. The way that the samples are selected is there are, in most countries, there's countries that have a registry of people in the country, so you go down the list and select the people from the registry. But in most countries, there are multiple stages of selection. So you'll select municipalities, and then from their blocks, and then from their household. Or sometimes you would select from a municipality, we'll select 3 households instead of just 1. Okay, so there's some level of stratification and some level of clustering that goes into place when selecting these samples. And we do this because of the way that the information is available. So in some countries there's a registry of all the people in the country, so it exists in the city. And sometimes even in the city there isn't. So for example, something that to me is very strange living in the US is that in the US you don't have to register anywhere and you don't have to have an ID with a picture. So there's a big debate over requiring a picture ID to vote. And people say you should have an ID when you go to vote. And some other people say, people have the freedom to have a picture ID and to register themselves with the government office. So we shouldn't force people to have a picture ID. So in the US, I don't know how it is in your countries, but in the US, you could say, there's people that say the government cannot mandate that I wear a helmet when I ride a motorcycle. So you see people riding in shorts, in a tank top, no helmet, in a motorcycle on the highway, and you think, huh? So anyway, so there's all this to say that the availability of information depends on the country, and what we have to do is get at the level where that information is available. We reduce costs by using sampling also, by doing systematic and stratifying. We also ensure representation of target population groups. We can achieve precision levels for target groups, and then also have some redundancy. So if you go to a big city, we don't select only 1 or 2 people from a big city. We'll select 100 people from a big city to make sure that we have some redundancy, and if somebody doesn't participate, that we still have people representing the different places, different groups within the big city. Questions about this? It's clear what we do. So the consequence is that we do not have a simple random selection of people. We have a random selection, but it's not simple random. So we stratify, we do systematic selection, and then we select clusters, and within those clusters we select multiple people. And this matters when we compute sampling errors. And here's an example of cluster sample. You see that here we have selected the same number of pixels that we selected here, but that image is not as clear as that. So when we do cluster sampling, because people within the clusters are more like each other, we're getting redundant information, but we're losing part of the big picture. So what we do is we select more clusters, smaller clusters, and then I hope you agree with me that this one, it gives you a better representation of what the picture is than that one. And that's the advantage of doing a systematic selection, which you ensure that you cover the whole spectrum of the picture, rather than do a simple random selection of the clusters across the country. Sometimes we do oversampling, so there might be areas where we want to get more information about those groups of people. So we do oversampling, that's what that looks like. But doing oversampling more people here doesn't affect the other areas. Okay, and that's a virtue of the weights. here's what happens when we exclude people, you know? That it depends on what we exclude. Sometimes excluding some things don't matter much to what the picture is, but sometimes excluding particular parts are very relevant to what the story that we're trying to tell. So, again, keep in mind, those of you that are in the field now, this is why we're so insistent to make sure that participation rates are high, so that we're not, and that you cover the population, so that you're not excluding important pieces that will, that would then yield your results biased. You know, that don't give you the quite picture of the country. Questions about this?
Just a comment, there are several countries, the northern part of Europe, that use the individuals as the smallest unit of analysis, right?
Yeah.
Like all the Nordic countries, the Netherlands and Belgium, and so, whereas Germany and many other countries have clusters, community or something as the smallest unit.
Right, yes, yeah. Yeah, that's what I was saying, that there are countries that have a registry of people. So you can go to the central office and say, give me a list of all the people in the country, and they'll say, well, you know, they wouldn't say it to anybody, you know, but people that do the sampling have access to those lists, and they select from them, yeah. But even in that case, they will still sort the people by, it wouldn't be an alphabetical sorting. It will be, I would assume that there's some sorting done by region of the country, by whatever other information is relevant that's available. Could be age group also, and then they'll do a systematic random selection of people from that frame. So it happens then that we go places, and then we select one person, and that one person is representative of other people like that person. So if you go to the example that I gave before, we have a large city, and we select 100 people. Those 100 people are representing the thousands or millions of people that are in that big city. So there's something called the sampling weights, and that's basically a number that represents the number of, in crude terms, it's the number of people that are represented by that person in the country. But it really is a number that is the proportion of people represented in the country that are represented by that person. Because the sampling weights, you can rescale them. So the sampling weights usually add up to the population size, but you can also rescale these weights to add to another number, and then that weight will be rescaled by a factor, and as long as that weight, the proportion of that weight to the overall sum of the weights remains constant, then that weight is proper. It's a good weight. So they take into account characteristics of the sample and selection procedures, and then once you do that, then you can stratify them, do stratification. You can adjust the weights for non-response. You can adjust know the selection probability of the different people, and you can also do checks, you know, against known statistics. So, for example, let's say that once you collect your sample, you realize that your sample is 40% males and 60% females. And then you look at your census data and you see it should be 49 to 51%. So then you could adjust the weights by multiplying one of them by a factor and the other one by another factor to ensure that the resulting weight is proportional to however many of those people exist in the population. Because that weight is actually the contribution that that particular case is going to have to the overall estimate. You follow that?
Do the weights you publish take into account all of
Yes, the weights are there.
adjustments for non-responses included?
Yeah.
Okay, that's good.
the main reason why I'm going through this whole explanation is that all of that is including the weights, and then sample weights must be used always to get correct population estimate, because if you don't do that, then you don't know what you get.
It's just some of them from time to time they are too big. Not for here, but some of them from time to time they are too big.
Yeah.
The weights.
Could be, yeah. So here's for example an example going back to the soup example. You know that fat has twice the amount of calories as protein. Right? You know that? So if you look at a product and it has 10 grams of fat and 10 grams of protein, then you multiply the grams of fat by 9, and you multiply the grams of protein by 4.5, I think it's the 4.5, and that gives you the number of calories, basically. See, now you know. But the point there is that 1 gram of fat, so if you eat 1 gram of fat, gives you twice the amount of calories as 1 gram of protein. Actually, 1 gram, so more like 1 gram. You know, so if you were to have the proteins and the fats contribute equally to the calorie count, you would be wrong. You would be consuming more calories than you think you are. So that's how the weights work. You know that. It tells you 1 gram counts 9 if it's fat, and 1 gram counts 4 if it's protein. And here's a little bit example of how we use weights. When we compute on weighted means, we basically sum the cases and divide by the number of cases. But when we have the weighted means, we are multiplying the values by their contribution. So 1 times 9 in the case of the fat, plus 1 times 4.5 in the case of the protein, divided by 13. So the calculations are actually different. They will give you a different number. Typical question that there's always somebody who thinks it or asks the question, so how different are they? And the answer is, it depends. The only way to know if the overall result is different or not is to do it both ways and compare. And if there's any difference, the right result is the one with the weights. So I'm of the thinking that if I have to do something twice to find out the difference, and one way is always going to win, then why not just do it once and move on? So using the weights gives you the right result. Using not the weights may or may not give you a similar result, but whenever there's a difference, the weighted result is the right one, so do it with one.
But
yes?
is that when you compute means, but when you use that data in regression analysis?
Always.
Yes, but also then use weights.
Always.
Yes. But then the number of observations are so many. So everything is significant.
Well, everything is significant if you assume simple random sampling. Because under the assumptions of simple random sample, you have that the standard error of a mean, for example, is equal to standard deviation divided by the square root of n. Okay, so when you use the weights, some software would actually put here the sum of the weights,
Which is not always correct.
which will give you a huge number, which is, well, I would say it's hardly ever correct. Because what you,
Usually,
yeah, so what you would do here, if there were a simple random sample, is that you would rescale the weights. The ghost coming in and out. If you rescale the weights so that they add up to the sample size, and then you divide here by the sample size. So some software, like SPSS for example, will put in here the sum of the weights, and then everything will come out significant.
Yeah.
software like SAS, you can specify what to put in here, and it would rescale the weights to put the number of cases here, so that wouldn't be affected.
But not in SPSS.
Not in SPSS. But two things. In SPSS, you could rescale the weights. Number one, make them add up to the sample size, in which case then it will be using here. So if you have case 1, 2, 3, weight, it's going to be 100, 200, 300, right? And what you do is you're gonna rescale weight. So you're gonna multiply this by 0.01. 0.01. Right? So you have 1, 2. You have 2. I'm doing this wrong.
No, I used to multiply them by 1 divided by the sum of weights.
Yeah, exactly. Yeah, that's what I'm doing. As I'm doing this, I'm saying I'm doing this right. So you will.
600.
So it'll be 600.
So it will be 1 divided by 600.
And how much is that? I don't know how to do that.
The first weight would be 0.16. No, the weight.
So this will be
First one.
0.5.
0.5.
And the other one is 0.33, and the other one is 0.17 round. Yeah. And if you introduce this one in any software, it will be correct.
Right. But the point here, I mean, I don't want to lose here. The point here is that these are the weights. If you multiply these by a constant, which in this case is going to be 0.16, if you multiply 100 times 0.16, it's going to give you that. 200 by 0.16 is going to give you that. 300 times 0.16 is going to give you that. So if you multiply the weights by all of them by the same number, the proportion remains. So this is 1/3 of that. This is 1/2 of that.
Now there'll still be a question when using them. Because actually, when calculating an indicator over the whole sample, the correct way is to introduce those standardized weights on the
Right.
website. In any software we will be introducing, it will be a correct analysis.
Correct.
But when I intend to extract a subsample
Yes.
out of 4,000, I want only 100 people, I don't know how to count them. If I count them by using...
You have to do it every time for the subgroup. Yeah.
it's...
Yeah, but then what this is going to lead to the procedures that we use, or that you should use to calculate the errors for the significance testing, are not affected by the sum of the weights. So, if you want to go on your own and do things on your own, then that's what you would have to do to readjust the weights. But the procedures that we use to calculate the standard errors, which is what we're going to be using to test for significance, are not affected by that. And I'm going to show you in a few minutes how that's done. So that you can run this with SPSS, or with Stata, or with SAS, and then you take the sign into account, and then the overall, the error is not affected by that, by the sample size or by the sum of the weights. But that raises an excellent point, because that we don't have simple random samples. And if we don't take that into account, then we're going to get into the problem that you're saying, that everything's going to be significant because we have thousands of people there. And that would be the case if you treat it as a simple random sample, which is not. So, how do we any other questions about this?
Just a comment. In SPSS, there's only 2 pieces of information you need to normalize the final student weights or the final weights. It's the number of observations and then the sum of
The weights.
the weights.
Yeah.
And that's the ratio that you use to normalize.
Basically, yeah. But as he was saying, that if that will apply to the entire sample, but then if you're gonna do it for
Yeah, you have to do it again.
boys and girls, you're gonna have to do it for each subgroup that you select. So you have to renormalize them multiple times. But the main point is that won't be necessary, given what I'm gonna show you, how I'm gonna show you to deal with the data, that won't be necessary at all, this normalization. So that's good, yeah.
That's true, yeah.
So we don't have a simple random sample, and we have a cluster sample where we go into a neighborhood, for example, and we pick 2 or 3 households from there, or from a city. Those people are more like each other than if I pick people from across the country. Okay? So a simple random sample of 5,000 persons from across the country covers the population diversity better than a sample of 200 clusters with 25 persons each. And that's that. Okay? The same number of pixels here covers the population better than that because these are clustered. A stratified multi-stage cluster design has more uncertainty associated with its estimates than an SRS of the same size. So the increase in uncertainty is directly related to the differences between and within the clusters. Okay, so if let's say all the clusters in the country are let's say the clusters are the blocks, city block. If they're all exactly the same, how many blocks do I need from a country? If all the blocks are exactly the same, 1, yeah. If every person within a block is exactly the same, how many persons within that block do I need? 1. But we know that blocks are not the same, and people within clusters vary. So how many people do we need given that clusters vary and the people within clusters vary? We need 1 cluster? Yes? No? More? 2? 3?
Depends on how many.
4? 5? How many do we need? 6?
Depends on how many.
Do we need all of them? I don't need all of them. I need more than 1, I need more than 2, more than 3. You need several clusters. And how many people from within each cluster? 1? 2? Same thing. Right? So where's the optimal point? The optimal point is the more clusters, the better. At some point, too many clusters are unnecessary. The more people, the better. But at some point, too many people are unnecessary also. Just like the soup. We don't want to drink the whole soup to see whether the soup is good or not. And we don't want to take all your blood out to see how your blood is. So somewhere in between is the magical number of the proper sample size for reporting the estimates at a certain precision level. So, but because people are different, and because clusters are different, if I were to do a selection today, and I select another one today, I could get a sample that varies a little bit. Okay? If all you are different, and I select 5 of you, and then I do another selection of 5, and I do another selection of 5, every time I will get a slightly different composition of you. And if I'm looking at your literacy results, every time we'll get a different literacy mean. Right? So how do I compute that? How do I compute the uncertainty around the score that I select? So that's why we talk about sampling, estimating sampling variance, and the factors that are going to influence that is, how big is the sample, how we sample, do I do systematic, to do simple random selection, how many people do I select, and the variability within the population. And I think I've touched on all these points throughout what I've talked about already. Is it clear? So, so the main point here, we do not have a simple random sample, and most analysis procedures, like standard SPSS, SAS, assume simple random samples should not be used, and we need special procedures to estimate the sampling uncertainty. So, because we cannot sample from the population over and over again, we use replicate units. So, the example that I was just given, how do I know, if I select 5 of you, how do I know the variability of that with respect to the population? Well, I have to select 5, and then 5 again, and then 5 again, and then 5 more, and 5 more, and compute the variance of those samples of 5. Yes? But then that contradicts what I said before, that if I do that over and over again, then my sample will be huge, and I want to get away with a small sample. So we use something called replication, and basically, think of this. Let's say I select 150 city blocks from the country, and they're all, and I compute my estimates with all the 150 city blocks, and I get a number. I take one block out and I recompute, and I get the same number. I put that block in, take another block out, and I recompute, and I get the same number. And I take that block out and put a block in, take another one out, and so I take pieces out and put them back in, and I always get the same number. What does this tell you about the city blocks? Are they all the same, or are they all different? They're the same. Okay? So I selected 150 blocks, and they're all the same. What does it tell you about the blocks that I didn't select? If I selected 150 from 10,000 and they're all the same, the assumption is that I got very unlucky, or that the other 9,850 are the same as the ones that I selected, right? Yes? That's the assumption that we make. And then, which means that if I had selected 150 over and over again, I would have always received the same estimate, or obtained the same estimate. Yes? So, let's take another example. I have the same 150 city blocks. I recompute something, and then I take one out, recompute, different number. Put the piece in, take another out, different number. Every time I do this, I get a different number. What does that tell me about the 150 city blocks that I have? That they're different. And if my 150 are different, how are the ones out there? Different also, right? So if I had selected 150 over and over again, I would have obtained a somewhat different result. You follow the logic of what? So replication, what the replications do is takes pieces out of the calculation, puts them back in, recalculates, and accumulates those differences. The bigger the difference, the bigger the accumulated difference, the more differences I have within my blocks, and the more uncertainty I have about my results. Because it tells me that if my things are different, if I had selected a different sample, I would have received a different number within a certain range. So, advantages of this replication thing, and I'm going to give you a bit more concrete examples in a few minutes. It's convenient to use because I don't have to go and select over and over again, but I can do it with what I have. Every time I do this, I can correct the effects of non-response in the weights, because we just got done talking about the weights, and the weights, I told you, it's the proportional contribution of the units to the overall. So I don't actually take people out and put them back in, but I actually zero out the weights, make their weight 0, or double the weight, or adjust the weight so that the weight contributes proportional to however much I want them to contribute that particular time. Really applicable to most statistics, and its advantage is very computer intensive because, as I said, I have to compute something with the whole thing, and then take pieces out, recompute, put them back in, take something else out, recompute, so I gotta do that over and over again. There's 3 main methods that I used in PIAAC. The jackknife methods, and there's 2 variants, and there's the balanced repeated replication with a phase variant. And here how that goes. So basically, when we do JK1, jackknife 1, we zero out some clusters, and then we adjust the others to account for that deletion. And these are, the R0 is the full weight, and these are the replicate weights, and that's a factor that I use to multiply the weight, the same factor that I was using here to multiply the weights. In the case of JK2, I'm actually doing something, this is done when we have stratification, and we select clusters within each strata, and then instead of adjusting everybody, we're going to zero out a piece and double the other piece, the other component of the cluster. And we do not do that systematically. Actually systematically, but randomly also. Sometimes I zero out the first, sometimes I zero out the second piece.
And which is the way you calculate the sample variances in PIAAC?
Like, depends on the country. Yeah, that's how I'm going to do it because it depends on the country. And here in the BRR, we have where nobody is actually taken out, but we actually increase the weight by 50% or divide it by half. Or divide it in half. Yes, somebody eating her hair already.
I have one question.
Yes.
Does this mean that for the Nordic countries where there were no clusters, because the countries are so small that it's based on, sorry, I don't know if I can form it, that the stratification is based on a person, this means that you would have to use the JK1 method,
Yes.
because you don't have the cluster.
I'm not sure specifically in the Nordic countries, but
Because their unit was a person rather than...
but it would apply to, so let's take a look. So the technical report would have that information. Nordic countries. So Nordic countries would be
Denmark, for example.
Denmark has JK1, Estonia has JK2, Finland JK2, Norway JK2. So no, I guess the answer to your question.
How do you tell how many replicates you have to are required?
So every there's this table that has the replicates. Let me go through this and then I'll answer the question was how can you tell how many replicas there are? So as you see there's depending on the country, it's JK1 or JK2, and it has to do with how the cases were selected. The details of exactly how they were selected in every country are in the technical report, and this is further proof that it's better to teach somebody to fish than to give them a fish. Because I don't know all these details, but I know where they are. So they're in the technical report. You will have somewhere in there the information about how the samples and why, so like the rationale for JK1 or JK2. So here I've used this example with 12 replicates because that's how big my slides are, So but those replicates could be, if you work with the PISA data, they have 80. If you look at the TIMS and PEARLS data, they have 75 replicates. If you look at something like the TALIS data set, the teacher learning study at the OEC, so they have 100 replicates. So the number of replicates are going to vary based on the number of clusters and the stratification, etc., etc. We did this, and then in the end, your error is going to be the variance, sampling variance is going to be the sum of the square differences between the replicates and the estimate, using the full estimate, multiplied by a factor which has the number of replicates. In the case of JK1, and in the case of JK2, you multiply by 1, and in the case of PRR, you multiply by this factor. So, questions about this? And notice that, I forget your name, that you had asked about the N. Notice that nowhere in there do we use the N. So when we use these methods, the sum of the weights is irrelevant. So it doesn't affect, because we're basically computing the estimates, and we're computing the difference between that full estimate using all the cases and then the estimate using a portion of the cases. And at no point do we divide by n. So that's why if you use this, when you use this procedure, that doesn't affect the significance of your result. So the other question is method and number of replicates that varies by country, and I'll show you the table in the technical report that has that information. So we've given you, we're gonna go over it. So there's two tools that you're gonna have. One is the Data Explorer, which has that information coded in, and then each data file has variables that identify the method and identify the number of replicates that are needed for that country. So there'll be there are variables called DEN reps, which is the variance estimation number of replicates. There's PIAAC, which is the fay factor in case there is one, and there's a DE method, which is a method of replication that's used for that country. So that's what you would know. So if you're going to be using Stata, for example, then it gets complicated, because then you're going to have to do your analysis country by country, specify the replication method and the number of replicates that you want to use.
But that is only when using status.
When you use Stata, yes. When you use SPSS with the IDB analyzer, that's part of the information that's in the file, and it will read it and take that into account. Same thing with the Data Explorer.
There are several weights in the file.
Yes, there are several weights. All those replicate weights are in the file.
So that means if we use Stata in the Explorer, we don't have to worry about it.
If you use the IDB analyzer and the Data Explorer, well, with Stata you need to. I don't know Stata, but you have to tell it the replication method that you want to use. Here's a. Let me step back and give you a more general statement, which is these are not simple random samples, and there's a stratified cluster design that you have to take into account at the time of computing your sampling area. These are the methods that we choose. Some people, usually somebody says, well, that's like bootstrapping, so we could do bootstrapping. And bootstrapping is reselecting and reselecting, and the reason why we wouldn't do bootstrapping is that each one of us will get a different number depending on the number of resampling that we do and the random selection that we have. So you would get different numbers, and then whenever you get a number that somebody else can't replicate, you know, there's a question of whether you did it right or whether somebody cheated somewhere. So when we do these studies, we say this is a method, and we know that anywhere in the world you run this with this method, you will be able to replicate exactly the numbers that were published in the reports. So there's no question about anybody cheating or you know. There's Taylor linearization approximations that some people use, and then if you have the cluster information, then you can also feed that into the program, and the program will calculate an approximate standard error, which when you have large samples, the numbers are about the same as you would get using either one of these methods, but as the samples get smaller, then you start getting differences. They're both estimates. Which one is better? I think they both have advantages and disadvantages. For us, better is the one that we can replicate. And that matches, you know, if I go to the technical report, if I go to the compendia, I can get that number. And I worked on in TIMS with the, and Pearls also with doing the data analysis. And one of my biggest fears was when somebody called me and said they couldn't replicate a number in the report, you know? It's like, because you always say, you know, what did I do wrong? You know? And you know, some people are like, you know, you check it yourself, but I was like, I gotta make sure that this is correct. You know, so you go and check. So that's why these methods are useful, but people use Taylor linearization approximation. The advantage of this method is that you can pretty much use it with any approach. You can do correlations, regressions, means, proportions, any analysis you can think of. That's the approach. You run the analysis with a full sample, and then take pieces out, rerun it, apply that formula, use the correct F factor for that, and that's your error. End of story. Questions about this? Okay, any questions about sampling? Sampling, variance estimation, etc., etc.
So, my question is that if we use the analyzer, and then we go to SPSS, we are safe, we don't put
Well, the question is if you use the IDB analyzer, which we'll show you later today, and the IDB analyzer will generate code in SPSS that will do this for you. So yes, you're safe when you use the IDB analyzer and run it, because that's what the IDB analyzer is doing. And the Data Explorer is also doing the same. The web-based application is also doing this.
Probably a silly question, but I'm looking at the sample selection methods, and there are a bunch of countries in the Northern Europe which took one stage of selection, right? And the question is the weight. You can't use it was kind of related, but they're not standard random samples, because they all have, like Denmark is standard random SRS within explicit strata. Within explicit strata, all the countries have used the standard random sample, but within explicit strata.
Right.
So it's not like
Yeah, so
SRS, like pure.
It's not a pure SRS,
No.
never.
No.
So they'll do something like, in Denmark, let's go to Copenhagen. From there we want to select 1,000 people, I'm making this up, you know, but let's select from Copenhagen 1,000 people, 500 males, 500 females. And they will select 500 and 500. And then they'll say, let's go to,
Aarhus.
yeah. And let's select from there 50 people. You know, so then in the end you have to put all this together, you know. And to make sure that those 1,000 represent however many people are in Copenhagen that are 16 to 65 in the overall Danish population. And you might say, in Copenhagen, I know, or in the south of Denmark, I want to select German-speaking and Danish-speaking people. And then you select amongst the Germans, and you select amongst the Danish, and then you have to make sure that you select, those are represented.
Eugene, would you mind just walking through the form?
Yeah.
I'm just trying to see how it would apply, like in a multivariate regression or something like that.
Yeah, you basically you calculate your statistic using the full sample, everybody there,
Yep.
and then, so using the full weight, and then you calculate the statistic using each one of the replicate weights. So if you're doing regression analysis, you will calculate your coefficient with everybody, and then calculate it using replicate 1, and then take the difference, square it. Then use replicate 2, take the difference, square it. Replicate 3, take the difference, square it. So if you run a regression, you would be running, and you have, you know, straight up 80 replicates, for example, you would run that regression 81 times. And then you would have here 80 differences, square, sum them up.
I get it. Don't want to do that.
That's what you have to do, I mean, to get there.
Yeah. So,
But I mean, I'm telling you this so that you know what's happening, why we insist on using the IDD analyzer, using the data explorer, or
yeah.
to take this into account. But nowadays the computers will do this in a minute. So it wouldn't be, you know, they will do this in a minute, literally, or less than that.
So PIAAC wouldn't provide, for instance, the SPSS syntax that would do that automatically.
Yeah, that's what we're gonna go. That's the IDB analyzer that we'll go over. And PIAAC will also give you the web-based tool where you can do descriptive statistics and some significance testing. You wouldn't be able to do regression, you know, but you'll be able to do percent of means, percent of people at different achievement levels, variances, and so on.